The next instrument we're going to look at is a compound microscope, and most of you are in the chemistry or biology fields and have used microscopes quite a bit. And I bet you have always wondered how they work. Well, there are two main lenses in a microscope. You have the objective lens, which is the one down here that really controls what power of magnification you have, and your eyepiece up here that also contributes to the magnification. And what's happening in a microscope is we have our object here on the plate, and the objective lens creates a real image near the eyepiece, and you want this to be about where the focal length is, and we'll look at that in a second. And then the eyepiece does the rest of the magnification to create a virtual image of this real image. And this is why when you look at a microscope, the image is upside down and inverted. If you try to move the thing to the right, it's going to move to the left. If you try to move it up, your image will move down. So you have to kind of get used to things being backwards under a microscope. So it consists of two main lenses, and these lenses are typically made of several lenses, just like a camera is, for the same reasons, to remove aberrations. And this gives a greater magnification than a single lens ever could. The objective lens has a short focal length, less than a centimeter, and the eyepiece lens has a focal length of a few centimeters. And one thing, since we're dealing with two lenses, we're going to look at this distance between the lenses. This is defined differently in different books, but generally manufacturers, we're going to want this to be about 16 centimeters is standard for most manufacturers. So lenses are separated by this distance L. L is much greater than either focal length, and typically L is about equal to the focal length of the eyepiece plus the image distance from our objective. And why do we want this image to be near the focal length of the eyepiece? Is because that's where we're going to have the maximum magnification. Even if it doesn't matter if we have a virtual image or a real image. This is the math we did for a converging, it was a mirror at the time, but the lens has the same math with a focal length of 5. So if we put an object or a real image at the focal point of a lens, we're not going to get an image. But you'll notice that we have asymptotes here that either side of the focal point we do get an image that is highly magnified, that we can get 10, 20, 30x magnification if we're really, really close to that focal point. So the general equation is we want the L to be about equal to the focal length of that eyepiece and the sum of the focal length of the eyepiece and the image distance. So the approach to analysis is the same for any two lenses, and we're going to approach it basically as just two lenses like we've done in the past. The image formed by the first lens becomes the object for the second lens. So there's nothing here, but since that's where the light rays converge, we can send those rays through another lens and reconverge them. The equations that are kind of specific for microscopes are these equations, and you'll notice that there are a lot of assumptions built in. So I am personally not a huge fan of these equations because the equations that we've used for the last couple chapters work, but these have some assumptions built in and can make our life a little easier as long as we make sure that those assumptions are followed. On the homework, you'll be asked to use one of these equations exactly once, and I will tell you to use this equation. But otherwise, go with the equations that we've used, the lens equation, the magnification equation. And we know magnification is equal to Q over P, but if P is about equal to F of our objective lens, then we can replace the Q with an L. So again, this is a lot of assumptions. And then our angular magnification for the eyepiece, as long as Q2 is at the near point for the person viewing the lens, and if you're looking at a microscope, you want that image to be at your near point. You want it to be as close as possible. So then we'll put that in there as our image distance and the focal length of our eyepiece. And if we combine those two equations, we get the total magnification power of the microscope. So we'll look at a couple examples where we use these equations. Well, another thing to consider, and we're going to talk about this a little bit more towards the end of the chapter, is the resolution of the microscope and why are there different types of microscopes. Well, the human eye is good for resolving stuff down to about the thickness of a human hair. You can see your hair, but you can't really see anything much smaller than a hair. And clearly, if you put your hair under a microscope, you can see it, and then all the way up to about 100 nanometers, which is about the size of a single cell. So you can see a bacteria cell pretty easily underneath a microscope. You can't see it with your naked eye, but you can see it under a microscope. But why does the microscope run into a limit? The microscope uses the same light that our eyes do, but it cannot see anything much smaller. And that's going to be due to the wavelength of light. It's going to have to deal with the wavelength of light that we're using. And to view anything smaller, such as atoms, proteins, viruses, we're going to need an electron microscope to view anything smaller, because the wavelength of an electron microscope is much, much smaller, and therefore we can see much smaller things.